I don't want to give too much of an introduction because I think we had an excellent keynote and the speaker explained very well why we need to be careful when we use machine learning system in everyday life. And I mean, just to be brief here, I went to Google News Search and tried to see what is currently in the news when it comes to when you enter like machine learning and fairness. And as you can see, in the United States, there are already like many approaches where people try to use machine learning systems to automate decisions that have been previously been made by humans. And there are different motivations for that. Mostly it's about cost, but also about efficiency and maybe some other metrics that you define. And so you say, okay, well, the US, they can do whatever they want, and probably in Germany, we might be more careful about that. But then, oh, actually, yeah, also here, like these systems, especially, for example, here predictive policing, are being used more and more to replace processes that were before carried out manually. So that means that it's more important than ever today to think about what it actually means if we use machine learning and data analysis to automate these kind of processes. And so what is fairness? Fairness is in principle not a technical concept. So people are being fair or unfair to other people. So it's nothing that falls directly in the realm of machine learning. But if we use machine learning to automate processes that were carried out by humans, we can make it a technological problem because the biases or the unfairness that is in the normal process can be automated or repeated using the technology. So machine learning systems, again, I want to say this is important that they are per se not fair or unfair, but they have the potential to be either one of them depending on how we actually make use of them. So, and personally, I think it's not always a bad thing to use machine learning or automated processes where we have been making decisions by humans before, because I think if we use these systems correctly, we have a large chance of actually eliminating many of the biases and many of the problems that were inherent in them. And so we just need to make sure that we use them in a good and a right way and in a careful way as well. So when people talk about fairness, they mostly think about discrimination. And discrimination is actually a treatment of a certain group of people that can be characterized by an attribute such as, for example, the ethnicity, the gender, or the sexual orientation in a way that is preferential or discriminatory in comparison to another group. And again, there are like many areas in our life where discrimination happens. Some of them are maybe less severe for the person being discriminated. For example, if I'm online and I'm trying to book a flight and my flight search engine shows me only like a very expensive price because it sees I'm on an iPad and thinks I'm maybe a user who has a bit more money, then this might be a nuisance for me, but it's not something that would like threaten my freedom or like have a very large impact on my life. But as there are more and more processes that we automate with machine learning, such as credit ranking, the decision who to hire or who to invite to like a recruiting interview, or even who to put on parole or who to like keep in jail or who to control or not as a policeman, these kind of decisions that are made by these automated systems tend to have a bigger and bigger effect on our lives. And if we want to think about discrimination in the context of machine learning, we of course have to have a mathematical definition because we cannot measure anything that we don't know how to define. And there are different ways to do that. So here I show one of the ways which has been established 40 years ago already and which is in wide use, which is why I also have it here as a first example. And it's so-called, and it's based on the probability of making it through a process as a member of a given group. So here you would have like a diagram. You can see there are two groups of people which are called x equals 0 and x equal 1. And they're going through a process which at the end has either a positive outcome or a negative outcome. And now we can ask ourselves, is there a dependence on the group membership of a given person on the success probability or the probability that he or she will make it through this process? And if we look at this, we can like make the quotient between these two probabilities. So the probability that the answer is yes and that the person is not a member of this group X, divided by the probability that the answer is yes, given that the person is a member of this group. And that's what we call the so-called disparate impact, or tau here. And this definition of discrimination has been used in like various contexts. For example, in the US, if you have a process that has a tau value which is smaller than 0.8, so 80%, this would get you into legal trouble. And again, this measure is not perfect. It's very simple in the way it's formulated, but it actually allows us to see a lot of cases of discrimination in our system. And the important thing here to notice is that this only makes sense if you assume that the people, which are either in the first or in the second group, are similar by all other metrics that are relevant. So if there are any differences between the people, this way of looking at discrimination would not be justified, so to say. An advantage of that scheme here is that it's very easy to actually implement or measure in practice. So the only thing that you need to do, if you have a process where you send people through, is to measure how many of them make it through from the first group, how many don't make it through from the first group, and the same thing from the second group. And then you make like this numerical quotient of these 4 numbers, and this gives you an estimate of the tau factor. So it's a really easy and very powerful way of measuring or seeing if there's any discrimination in the process that we are designing. As I said, it's not a perfect measure. There are alternatives. So the disparate impact is a so-called group-based measurement. So it only looks at different groups in respect to each other. And so it wouldn't be able to see some forms of discrimination. For example, I could imagine still having parity between the 2 groups, but only choosing like the worst people for members of one group that make it through the process, thereby discriminating people that, for example, have better attributes in this protected group. So I can still do some discrimination that wouldn't be seen by this kind of measure. And other measures which do not have this fold are so-called individual-based discrimination or fairness measures. So the idea is shown here. What you need for that is to define a distance function that would give you a distance between 2 of your individuals in the data set based on the characteristics or attributes that you deem acceptable for comparing individuals. So it should, of course, not include any of the attributes which you do not want to discriminate people by. And then you can take this distance and compare it to another distance function that gives you the distance between the actual treatment that these people are undergoing through in the system. And you can normally find, if your system is not discriminating, you will be able to find a constant that is such that people which are similar will also be treated similarly. And this definition makes it easier to find discrimination which cannot be captured by the group-based approach. I will not talk about this in this talk because it's a quite sophisticated concept, and the problem is, of course, that you need to find a corresponding or good distance function, which is not always easy, and therefore I will continue with the normal disparate impact-based discrimination measure. I just wanted to be sure to say that there are other approaches to measuring discrimination in these kind of processes. So instead of continuing with the theory, I want to now go with you through the process of actually designing a system that automates something that has been done manually and that also has a large impact on the lives of people. And you know that I showed some news article about predictive policing. So there are lots of projects in this area throughout the world, and the goal is usually to kind of direct the efforts of police officers so that they have a higher likelihood of finding criminals, for example. And there are, for example, programs for this in New York, but also in Germany. And we could ask ourselves the question, can we design an algorithm that would help a police officer to, for example, make a decision if he should or she should like control or frisk someone, so like pat down someone and see if that person is maybe hiding something. And of course, in order to do that, we would need to do like some really large-scale social experimentation on people first to get all the data. And this sounds like a crazy idea to do, of course. But fortunately, somebody already did that work for us, because in New York, they had this so-called stop and frisk program, which was a program running between 2004 and about like 2014, which basically gave the right to a police officer to just stop someone in the street and then perform a search on that person. So, and the reason for that stop could be very vague. So the police officer basically had a lot of leeway of determining which people to stop and which to frisk then. And you can see there are many hundreds of thousands of people that have been, even millions of people that have been frisked in this time frame from 2003 to 2014. And every time this happens, the police officers was required to make a report about that. So there's a lot of paperwork with a very detailed analysis of each case that we can use to train an algorithm against. So here's actually all the input variables that we have available in this data set. You can see I tried to group them roughly by things that are related to the appearance of a given person, things that are related to the behavior of a person, and things that are related to the circumstances. So you can see in the appearance column you have such things which, for example, the age of the suspect, the weight, I don't know if they have a scale there where they measure people, but somehow they determine that. The height of the person in feet, so 5, 6, or 7, for example. The eye color, the race, the sex, the build, and other attributes. And you also have like behavior-based information. For example, if that person reacted evasively to questioning, whatever that might mean. If this subject seemed to be acting as a lookout, for example, or if the subject changed the direction when seeing the police officer. And finally, you have other attributes which are related neither not to the behavior or not to the appearance, but to the circumstances, what I call. And there are such things as if the frisking was made inside or outside a building, if it was made in a metro station, at which time of the day it was made, in which precinct. So this corresponds to roughly to like a block or a neighborhood in New York, and some other things. And of course, it's really difficult to say what kind of like interpretation lies beneath that data. And for example, if I see this like wearing clothes commonly used in a crime, I don't know what exactly defines that. So, but let's assume that these things are all like objectively or mostly objectively taken, and that we can use them as a basis for our algorithm. So that leaves us with like 40 different attributes almost that we can use. And we have in the data set also 3 attributes that we can use for training. The first one is the fact if the person described here has been frisked, so it has been searched. And the second one is that person has been arrested subsequently. And the third one is if that person has been summoned to come to a police station afterwards. So this will be our target data, so to say. Now, in order to make an algorithm for this, we need to have a process model first. And this model is shown here. So you would have all the people that are in the database. And then we have a choice. We can either choose to frisk that person or not frisk that person. And if we do that, then afterwards there might be some evidence that leads to an arrest of a given person or not to an arrest. So in the next slide, what I will be calling a true positive is, so to say, the case when we have a person that we frisk and that we also arrest because there's maybe some evidence, whereas a false positive is a person that we frisk but that we do not arrest, so a person that is innocent, so to say. And correspondingly, there's here the true negatives, so people we don't frisk and we don't arrest. And there's also here the false negative, which is like we don't frisk a person, but we somehow arrest it, which is, I don't know even how that works in the data, but yeah, it's also a case that we have to take care of. So now we want to build a system that decides actually whether to frisk someone or not. And doing that, we want to try to maximize the discovery of criminal people while not ideally bordering the law-abiding citizens. And of course, we also do not want to discriminate against certain groups of people. In order to do that, we first need to choose a numerical loss function that we can train our algorithm against. And here again, we have to make a choice. So as we will see later, most of the people that are in the data set actually didn't commit any kind of crime or have any reason to be arrested. So this means that our system will have a lot of false positives probably because people will get frisked that don't have done anything wrong. And we need to take to balance that against the probability of not frisking someone who might be a criminal. So we can do that by using a so-called weight parameter in our system, which would tell the algorithm, okay, if you've frisked someone who is not who didn't commit a crime, you will get a penalty of -1. But if you frisk someone who is then arrested, you will get a reward which is equal to alpha. And this sounds abstract, but you can actually reformulate that as this. So it would basically say to the algorithm, it's okay to frisk alpha plus 1 people if you find 1 criminal then, because then your score is still going up. So if I frisk 10 people and I find 11 people and I find 1 criminal with an alpha of 10, then the score would stay the same. So in a sense, we are going here from a state where like police is very polite and not checking anyone to like a total surveillance state where everybody is under suspicion and your life is basically an endless TSA security line. Now, before we start designing the algorithm or training it, we want to have a look at how actually the data is like, and if there is any discrimination inside the training data that we're using. And as we saw before, the people here, there's a so-called race attribute, which is a term that I don't like at all, by the way, that gives the race or the ethnicity of the people in the data set. And you can see we have, for example, black people, white people, this is, I think, black Latin American, white Latin American, other or unknown, and Asian people. And for each of these groups of people, we have first the probability or the frequency of them being frisked in this data set. And you can see for black people, for example, 50% of the people that were stopped were also frisked. Whereas for white people, only 35% of the people that were stopped were actually frisked. And you can see already there might be some bias going on. And now, of course, you could argue that, maybe these people in one group being stopped were acting like suspiciously, so there was a good reason to stop them. And in fact, you can answer that question by looking at the second row here, which gives the probability of an arrest being made after the frisking happens, you know? And you can see that, for example, for black people, in 80% of the cases, no arrest is made, whereas for white people, in 73% of the cases. So that means more of these white people here get arrested than of the black people, which would indicate that there's a slight tendency to frisk more black people, even if it might not be justified. So there seems to be some discrimination going on here already. And again, this is open to interpretation, but it always depends on how you measure similarity and fairness in the system. But for me, there's certainly some discrimination in this data. Okay, so now, nevertheless, let's use that in order to build a model. And so what we do here is a multi-step process. So we first take our input data. I used only the data from the year 2003 for that. I selected the different attributes. Those were mostly like either like yes, no, or binary attributes, like was it inside or outside or in an NTA station or not. But some of these attributes, they were also continuous or categorical, like the race, for example, or the ethnicity, or the time of the day. And for these attributes, what we did was a so-called one-hot method, where we define a category for each possible values of these where we define, an attribute for each possible values of a given categorical attribute. So if you have, for example, 10 ethnicities, we would define 10 new attributes, which were called black, white, Asian, white, etc., and would give that attribute a 1 if the person is a member of that group, and a 0 if not. So having done that, we get about like 170 categorical or yes-no attributes that we can use for the training. We can then just train a simple classifier. In our case, I choose logistic regression from scikit-learn, which is easy and works quite well on this kind of data. We then split the data set into a training and a test set. In this case, we did that with a 70-30 split. So 70% of the data was used for training, 30% then for testing. And we will generate various models for a range of these alpha values, seeing how the algorithm behaves. Now, the first thing that we want to do is to see if we can predict if a given person was frisked in the data set, given all the input attributes that we have. Now, what I will show you in the next 15 minutes will be a lot of these charts. So I wanted to take a moment to explain exactly what they show and how to interpret them. So what you have here is, on one hand, the false positives by the algorithm and the false negatives as a function of this weight parameter alpha. So we start with a weight of 0 here. Basically, that would tell the algorithm only frisk people where you're 100% sure that they might get arrested, to a value of about 15, where the algorithm would be able to frisk 15 people if it finds at least one criminal, so to say. And here I plot this line shows the total number of people in the data set, about 40,000 or slightly less than 40,000. And this other line shows the number of people that have been frisked. So, and as you can see, I hope you can see it, there's a blue line which represents the choice of the algorithm, and there's a green line which we use for comparison. And the green line basically chooses the same number of people as the algorithm, but it chooses them totally randomly. And this is the benchmark that we use to test our algorithms against. Because if we want to build a system, we should be sure that it's at least as good as a totally random pick of people, you know? Because if we are not even as good as that, we couldn't have any justification for using this algorithm. We could just like roll the dice, so to say. And you can see in this example, which I show, the algorithm is slightly better than picking people at random. So you can see there's a difference between the green and the blue curve for the false negatives, which means that we are identifying some people that are being like frisked in the data set using their attributes. But there's also some room here between the green line and the blue line, which means that the algorithm has categorizes some people as being frisked who are not getting frisked in the data set. And this can be explained by the fact that the algorithm will, at each point here in the graph, choose the parameters which have a probability of increasing like the number of frisked people more scaled by the weight factor more than it increases the number of false positives. So for example, if alpha is 3, then the algorithm could try to increase the number of frisked people it finds by generating about like 3 false positives. So it will, in that case, so to say, trade the false positives for the true negatives. And the dilemma of our algorithm of designing the system then comes basically to the point of choosing an alpha parameter that is good, and then seeing what that which kind of effect it has on our system. So the first case, just as a benchmark, is a simulation where we only give random noise to the algorithm, so we don't provide any good information, and we see what happens. And as you can see, as the algorithm doesn't have any clue who to pick, so it can just pick people randomly, what it will do is that at the beginning, where the false positives have a very high penalty compared to the true positives, it will just mark everyone as innocent, because it would say I don't have any chance of like finding the right people with a good probability, so I will just not frisk anyone. But as we increase the alpha factor, at some point, so in this case about like at a value of slightly more than 1, the algorithm say, okay, now given the score, or the alpha value, if I frisk everyone, my score will still be higher than if I frisk no one, because the people that are being frisked, in this case like 50%, will generate more score than the penalty I get for the other ones. And so you can see at this point it completely switches its strategy, and suddenly everyone is a suspect. Okay, so this is just to give you an idea of how changing the alpha value can change the behavior and the results of the algorithm in this context. Now, let's finally give some real data to the algorithm and see what it can do with it. So now what we're doing is to provide all the input attributes that we have, that we discussed before, to the algorithm and ask it to predict the frisk value. And you can see this is actually working quite well, because we have a lot of space here, a lot of signal between these two curves, which means that the algorithm is much better at picking people than just a random chooser, so to say. What we also have, though, is a large number of false positives. And you can ask yourself, why is that? I mean, we explained the reason before, but of course the more interesting question is, what is the effect on like people from different groups. Is there any bias now in the system? Because we saw that there's some bias in the input data, and the question is, can the algorithm actually pick that up, or will it pick it up? So in order to quantify that, we now plot here, again as a function of the weight parameter alpha, the percentage of the people that are being frisked in each ethnical group. So again, we have like white people, black people, Asian people, Latinos, and others. And we plot the percentage of people in a given group that have been chosen for frisking by our algorithm. And as you can see, unfortunately here, there is like a large discrimination going on, because the probability of being frisked if you're in this group here, so if you're a white person, is much lower than, for example, if you're in the group of black people. So what this means is that effectively our algorithm has picked up this bias that is in the input signal and reproduced it in order to make a better prediction. Because by using this biased approach, it can increase the score that we gave to it by discriminating against these people. So where does this bias actually come from? You know, and we can answer that question by trying to like change our algorithm a little bit. So now, instead of trying to predict if a person is getting frisked or not, we will try to predict if that person belongs to the black group. So given all the other input attributes. If we do that, we make again the same plot as before. So now only we plot not the percentage of people being frisked, but instead the percentage of people categorized as black. And as you can see here, for most of the weight parameters alpha, there's a large difference that the algorithm can pick up between white people and black people. So for example, at the value of 2, about 90% of all the people in the sample are categorized as black, whereas the ground truth is only 50% if you would choose people at random. So that means that there is some information that the algorithm can use to actually predict the ethnicity attribute of a given person. And this, in turn, is the basis by which the algorithm can then discriminate against these people. So now we've seen that it exists, so the question is, how can we eliminate that? Again, there are different approaches here. One approach would be, of course, to identify the attributes that are problematic in the sense that they can predict the protected attribute as the ethnicity, and then remove these attributes from the data set. And this is something that we could do with like the information that we generated in the last step, and it's usually a good idea if you can clearly identify some problematic attributes. The problem with that is, of course, that usually the attributes that we remove do not only contain information about the protected class, but they contain some other useful information about our prediction problem. So by removing them, we're also decreasing the fidelity or the accuracy of our algorithm. The second possibility is not to remove attributes, but instead to remove whole data points. So if you can somehow identify which data points or which individuals might have been subject to discrimination in the data set, we could then just remove those data points and do not give the algorithm reason to believe that, or reason to like discriminate against these people, because the discrimination is effectively or like to a large part removed from the data set. And this is also doable, but the problem is then again that we might also use other useful information that we can use to improve the accuracy of the algorithm. There's a variation of that approach which consists in not removing the whole data point, but modifying some properties of that. For example, you could like add statistical noise to a given attribute of a person to make it less correlated with a sensitive or protected attribute. Again, here the problem would be that we're also not only like erasing this correlation between the protected attribute and the normal attribute, but also other useful correlations that are in the data. So again, this is also not like a perfect way of doing it. The third way would be to not change the input data, but instead put a constraint on our algorithm. So we could, for example, give it an additional loss function that is proportional to the amount of discrimination that it produces, and then ask it to optimize the combined loss function of our accuracy and discrimination measure. And basically what we would tell the algorithm would be to like restrict the parameter space to some areas which contain the allowed solution, and then some space where they are the so-called forbidden solution. Again, this is not a perfect method because it only provides, so to say, like the minimum viable solution to the problem, but it's not guaranteed to deliver the best solution with no bias at all. So it will only do normally the minimum that is required in order to meet the criteria and then stop there. So it's not really a good approach if you really want to get rid of the discrimination in your algorithm. And of course, the final thing that we could do is to simply change the target attribute and to see if we can find something that might be more suitable and contains less bias. Now let's try the first method. So what we do again here is take the different attribute values and then try to predict whether a person is a member of this black group. So we do this for the behavior-based attributes and for the circumstance-based attributes. And as you can see here, the behavior-based attributes have a much harder time predicting actually the group membership than the circumstance-based ones. And the explanation that I have for this is that behavior is of course less correlated to like appearance, whereas the circumstance also contains, for example, the precinct, so the location where the person was frisked. And as you have different communities in New York, and in some communities you have like more black people than others, it's of course useful information that can be picked up by the algorithm to again give a probability estimate of how many of the people here in this area might belong to this given group. And now we could, like, based on this information, for example, say, okay, the behavior-based information seems to not have a very large bias in this sense. So let's try to use that one. And that's what we do here. So instead of using all the input features as before, we just use the behavior-based ones. And we again have a look at the false positives and the false negatives. So you can see the plot looks like a lot more bumpier now. The reason for that is that there are a lot less features in there. So before we had like 120 features, now we have only maybe 10 features, and you can think of it like that every feature has a certain probability by which it can like predict a membership of this frisk group or not of a person. So as we move this alpha parameter, at first the algorithm can only use the features that are the most predictive. And as this parameter increases and the penalty for false positives decreases, the algorithm can then sequentially use also attributes which are less predictive, but which can like produce a little, so to say, increase in the true positives. And you can see that there's still some signal between the two curves, much less signal than before, of course, as you can see here. And there's also like, in some areas at least, less false positives. So let's see what this does to the disparate treatment between the individual groups. Here again I have the same chart. So the number of people in the frisk group grouped by their ethnicity as a function of the weight parameter. And as you can see now, if we compare this to our earlier result, you can see that there's still some discrimination going on, but it's less pronounced than before. So this means by removing these problematic input attributes, we were able to reduce the discrimination done by our algorithm. So this is good, of course, but still not perfect. So let's try the other strategy that we discussed, and that is changing the target attribute. So instead of now using the frisked value, so if a person has been frisked or not, we will use instead the fact if that person has been arrested. Because the reasoning here is that it's always possible to frisk someone if you want that as a police officer, but it's harder to arrest someone if that person didn't commit any crime or is innocent, so to say. So what we would expect is that there's less bias in this target attribute than in the other target attribute before. Okay, let's try it. So here's again the result of that. You can see we still have some signal here, so the algorithm is still able to pick out the people better than a random chooser. And at the same time, we also reduced the number of false positives. And the reason for this is that now, as we have many less people in the target group, so only, I think, 10% or 20% of the people that are in the database were arrested, whereas 50% of them were frisked. So it doesn't make as much sense to trade the false positives to for the true positives for the algorithm, so to say. So it's harder to actually just like frisk more people and then like get away with that by also finding some people that might get arrested, because there are not so many people that are being arrested in the data set. And so the algorithm here has to be a bit more careful, or it cannot like trade as much as before. Okay, looking at the bias in this resulting data, we can see that now we have a much better result than before, because you can see that there's, for example, no discrimination against black people, which have in fact even the lowest probability of being frisked, but there's still, for example, for this group here, some residual discrimination going on, though all the other groups seem to be like very close to each other in terms of the discrimination metric. So this solution, which uses both a different target attribute and less input attributes than before, is much better than our original big data solution, so to say, where we just like give everything that we have to the algorithm and try to make a prediction with it. So as a result, you can see here the better but still imperfect treatment of people by the algorithm. So this is the result of our method if we choose, if we just put ourselves at the value of 7 here. So we make this choice to say, okay, we want to be at this point and like have a false, like a frisking probability which is comparable to the original data, and like get as many of these criminals as possible. And then we see the result here again as this flowchart, and you can see now that concerning the arrests that are being made in each group, there's much less difference as compared to before. So here the probability is in most cases about 80%, which means that at least on this group measurement approach, there is no large discrimination between individual groups. There is still some discrimination, as you can see here, for this one group of like black Latin Americans, which are getting frisked significantly more than the other ones. So this is something that we would also need to take care of if we would design a real system here. Okay, the takeaways from that. Well, we can say that, as we saw, like most of the training data that we use in real-world algorithms will contain biases, and some of these biases will be implicit and also not easy to recognize. So if you want to see them, we really have to look, and we have to use like these correct measures and these correct methods to identify them. And in order to protect the people from the discrimination, we need to do something which is a bit paradoxical, because we actually need to like record all their sensitive data, you know, because today most of the people that are designing data like these algorithmic systems, they say, okay, we couldn't discriminate against people because we do not even record these sensitive or protected attributes. And this is the wrong approach, because if you don't record them, or if you don't have them, you can never measure if there is any discrimination in your system. So in order to do that, you really need to have this data. And finally, as I hope I could show, there's also not only a chance of like making things worse using algorithms, but also like a huge chance of making things actually better. And as we've seen, if you like are careful in how to design a process or an algorithm, we can actually produce a result which is less biased than the original one, even when using originally biased input data for that. Now, as a final point,
sorry. Running out of time. I have to
okay, I'm done
right
now.
here.
Just need 1 minute.
And thank you very much for this really interesting talk. Okay, maybe not. And given the delay of this talk, I'm going to take 2 questions. And please be brief. I'm sure you're going to be around. So if you have more questions, you can just approach them afterwards.
Hi. I was wondering, so what's in, like, what do you would advise the police to do then? I mean, how do you translate your findings into the real world?
The findings here, so as I showed, there are like different ways to deal with these problems. What you have to do is, of course, be sure that you choose your input data well, and that you like test it for biases and discrimination. And then you need to like, actually this was on my last slide, which I was not able to show. What I imagine a machine learning system to be is to have, in order to be safe, is actually a way to get this protected data in order to like sanitize the input data, and then also have a way to audit your algorithm or the outcomes of the algorithm using a fairness metric like the one we discussed in the talk.
I don't mean in the data. How do you give that back to the police? What do you tell them?
Well, I mean, there are different vendors of these systems, and what I think is important and what is not like done today is that the algorithms and the target attributes that they are trained for are not public. So in order to have a system where you would actually have some way to like see if there's discrimination, you need the data to be like at least partially open, and you need the algorithm to be open. Does that answer the question? No?
Hi. So quite a quick question. So one of the questions around when we detect discrimination, let's say as in the Google paper between the orange population and the blue population, their approach at the end was, okay, let's create a model that works as well as you can and then set different thresholds for the two populations. That is computationally very elegant, politically very difficult, because you would effectively be creating a system that actively discriminated positively with one population in order to compensate for the bias in the data. Could you comment on how you actually design systems that solve the problem, just rather than just the identification part?
So I'm a big fan of individual-based measures of fairness. So there, of course, the problem, as I explained, is that you need to find a measure that like includes the right attributes in order to compare two people, and then the rest of it would, so to say, be automatic, and then you could just design an algorithm that optimizes the target value by also following this condition that you have like not that similar people are treated similarly. But I think there's not a universal answer to that question. In some cases, you want maybe to do some affirmative algorithmic action, in order to treat people in a certain group better, or give them a bonus, so to say, in order to reduce the discrimination that they're subjected to. So, and depending on what you want to do, you need to define your target function and your input attributes in different ways. So I think there's not a universal approach to fairness where you can just put in your data and then you get a fair result out. So you always have to think about what fair is, what output attributes you have, and what metrics you want to use to measure that.
Okay, perfect. Thank you very much, Andreas. So we have 5 minutes left